Okay, so let's check out this problem and kind of see how all this works and plays, and we'll look through a couple different problems as well, and hopefully that will help us solidify this. In reality, guys, I want you to recognize that really what we're doing is no different than what we've been doing with equilibrium. We're now just applying it to different types of situations, in this case aqueous acid-base situations, to calculate things like pH, pOH, percent dissociation, so on and so forth. So really this is a extension of equilibrium. The rules of equilibrium have not changed in any way, shape, or form. It is still just equilibrium. So don't let this stress you out, okay? So lactic acid is a waste product that accumulates in the muscle tissue during exertion, leading to pain and a feeling of fatigue. In a 0.100 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate the value of the Ka for this acid. So what does all this actually mean? It means an equilibrium problem, but we're not given Ka. We're being asked to solve for Ka. So what is Ka? Ka is the expression of hydronium, or hydrogen in this case, just because I don't have water written here, though I usually do, times the lactate ion over the lactic acid. And this is all at equilibrium. So what does that mean for us in terms of calculations? In terms of calculations, we need to figure out what are the concentrations of these species at equilibrium. Well, how do we do that? We set up an ice table. No different than what we've done in the past. So I, C, E, initial is 0.100 of this guy, 0 and 0, minus X, plus X, plus X. Okay, from there, 0.100 minus X, X, and X. But we don't have a K value to solve for X this time, so this is a little bit different in terms of process. What we do have is this guy right here. And what we're basically being told here is that 3.7% dissociates, which is technically our X value. X is 3.7% of our initial value. So if we think about it this way, percent dissociation equals X over our initial concentration. So we can solve for X, of course this is times 100 too if we want to include that, by basically going 3.7 equals X over initial 0.100 times 100, and basically solve that out from there. So let's kind of work through this, or you take a second, you solve for X, see what you... Okay, so when I go through and solve this guy out, what I'm getting is an X value that is equal to 0.0037 molar, which should make some sense, because if I take 0.0037, put it over 0.100, I'm going to get 0.037 times 100, gives me 3.7%. Regardless, just always go back and kind of double check your math, make sure it logically makes sense. So at equilibrium, X is 0.0037, and that's going to be true for our lactate ion as well. And it's also going to be true for over here. So 0.100 minus 0.0037. And we actually do have to calculate out this value in this case because we need the actual equilibrium value to be able to solve for our K value. So at equilibrium, there is 0.0963 molar of the lactic acid left in solution. So from here, we calculate our Ka value. So Ka is going to be equal to 0.0037 times 0.0037, and yes, you can just write the square there if you want, over 0.0963. And that is going to basically give us, calculate it real quickly, I'm getting a Ka value of, Smartboard being silly right now. There we go. Let's just try writing. There we go. 1.4. We'll go out to 2 sig figs because that's what it looks like. 1.42 times 10 to the negative fourth is our Ka value. So not too hard. Pretty easy actually. Just again, it's an application of equilibrium and taking it that one step further. So let's keep looking at some more problems. Alright, so this is a warm-up I used last year. I want you to go through and you solve it. So pause the video right now, then I'll walk through and solve it. But I want you to pause, you try to solve it, and then we'll come back and reconvene and see where we all are. Okay, so if we were solving this, the first thing we're going to do is set up our equilibrium equation. And sometimes this is given to you, sometimes it's not. It really depends on the problem, but most of the time this is pretty easy to figure out, because if it's a base, all you're doing is moving the hydrogen towards the basic substance. If it's an acid, you're taking the hydrogen away and putting it towards water. So we end up with this. From there, we set up our ice table. And we have 1 molar. Going to get rid of the water. 0 and 0. Minus x, plus x, plus x, and then 1.0 minus x, x, and x. And we solve it by setting up our KB, 4.38, sorry, not 4.8, 4.38 times 10 to the negative 4th is going to equal x times x, or x squared, however you want to do that, over 1.0. So what we actually end up with is that 4.38 square rooted. So 4.38 square root, and I am getting my x value to be 2.1, because again our concentration is only 2 sig figs, so we'll do 2.1. Times 10 to the negative 2nd molar. And again, that's for hydroxide. So the first thing we're going to do is calculate POH. So we take the negative log of that value, and we get just below 2 as expected. So 1.68, if it's going to write, which it's not. And then pH, we take 14 minus that answer. Sorry about that. It was being spazzy. Now we got that up and running. All right, pH then equals 1.68 minus 14, or 14 minus 1.68, I should say, which gives us 12.32 as our pH. Okay, check to see if you got the same thing. And let's keep going. Okay, what is the KB of a base who has a pH of 9.51 and a 2.25 times 10 to the negative 2nd molar solution? And then what is a percent ionization or dissociation, same term? And this is a little bit different than something we have solved before. So in this case, notice we're not really given an actual substance, and that's okay. It doesn't really matter what the substance is. It's just some type of base, so I'm just going to call it B. We're reacting with water. What does a base do? It steals the hydrogen, so we end up with HB plus, and hydroxide, OH minus. From there, we set up our ice table, I, C, E, and that should always be the first step, is to set up your ice table. So we are told that we have a 2.25 times 10 to the negative 2nd molar. We don't care about the water. 0, 0, minus x, plus x, plus x, and we have 2.25 times 10 to the negative 2nd, minus x. I'm just going to go ahead and get rid of that. There we go. X and x. So what in the world do we do from here? We're not given a percent dissociation. We're being asked to solve for it. We're also not given a KB. We're being asked to solve for it. So what do? We use this information right here. This is very common in basically College Board, college chemistry, general chemistry, whatever types of problems you want to think about, where you're having to work backwards a little bit here. We have to recognize, what is pH? Well, pH would give us the concentration of hydronium ions if we use the equation. Do I care about hydronium? No. I care about hydroxide. So what do we actually need here? What we need is POH. And how do we get POH from pH? We just subtract it from 14. So 14 minus 9.51 gives us a POH of 4.49. Why is that helpful? Because we can get the concentration of hydroxide from our POH value. So let's go look at that. Scroll down a little bit so we got some more room. POH, which is 4.49 in this case, is going to equal the negative log the hydroxide ion concentration, which in this case is our X value. So all we have to do is solve this up. So we're going to bring the negative over. Okay, inverse log is 10 raised to So 10 raised to the negative 4.49. And that's going to give us a hydroxide ion concentration equal to 3.24 times 10 to the negative fifth. Okay, well, why is it helpful? That is our hydroxide ion concentration, which is our X value, so that goes in here, here, and all the way over here. Now we have enough information to calculate KB in this case, as well as our percent dissociation. It doesn't really matter which one you solve for first, it's just solving for it. So we have to recognize that at equilibrium, let's solve for KB first, KB is going to be equal to 3.24 times 10 to the negative fifth times 3.24 times 10 to the negative fifth over 2.25 times 10 to the negative second minus 3.24 times 10 to the negative fifth, because remember, we actually have to solve that out. So when we're solving for x, mathematically, we can assume that that value is negligible, and we can look at 10 to the negative fifth and say it's negligible compared to 10 to the negative second. But in terms of calculating KB, we actually have to know what that value is. Okay, so let's see what we get when we calculate this guy out. Okay, and when I go through and calculate this, I'm getting a KB value equal to 4.7 times 10 to the negative eighth, so very small. Okay, the next thing it asks us to do is do percent dissociation. All right, let me see if I can get this thing. It's not calibrating very well. It's being spazzy. Sorry, guys. All right, percent dissociation again is going to be, there we go. Nope, that's too low. Come on. Going to be percent is going to be equal to how much dissociates, which in this case is our x value, so 3.24 times 10 to the negative fifth, over our initial concentration of 2.25 times 10 to the negative second, and of course that's going to be times 100. So when we calculate that out, let's see what we get. We get 3.24 times 10 to the negative fifth divided by 2.25 times 10 to the negative second times 100. I am getting a percentage of very small, which is what I would expect based off that KB value, of a percent equal to, let's see if this thing will write. There we go. 0.14%. So a very, very small percentage even after all that work. It's not very big, which again, we would expect that from that small of a KB value. Okay, so that's just kind of some of the different ways we can solve these out. We can work through a couple problems from here, and that's it for right now. Thanks, guys.